In our previous lessons, we talked about the concept of the first derivative and how it measures the rate of change of a function. And now we're going to talk about in this lesson what's called higher order derivatives. And higher order derivatives go beyond finding the rate of change of a function. Higher order derivatives actually tell us about how the rate of change itself is changing. It's the rate of change of the rate of change. So in this lesson, we're going to talk about higher order derivatives, the notation, how to interpret it, and we're going to practice some examples. Let's first look at the notation. We have f prime that indicates, that's this right here, that indicates the first derivative. And it indicates the first derivative because I have one little dash up here where the exponent would be. Now, if I see a double prime, that means you're taking the second derivative of the function f. So after you take the first derivative, then you're going to take the derivative of the derivative. That's the second derivative. If you go ahead and take the third derivative, then you'd see a triple prime here. It's not very often that we go past the triple derivative, but if we do, the notation for that, once we get past 3, you would have a little 4 up where you would have your exponent with parentheses around it, and that would indicate the fourth derivative, the fifth derivative, etc. Now, when we're using the Leibniz notation, the way that that's going to show a higher order derivative is instead of having dy dx, you're going to have where the n is here, the derivative that you're taking. So if you're taking, say, the second derivative, you would see d and then a 2 up here where the n is, and then y over dx, and then up here where the n is, you would have a 2. So that's what it's going to look like when you're taking a higher order derivative with the Leibniz notation. So let's look at this first example. We're given the function is 3x to the fifth minus 2x to the fourth plus x squared minus 10x plus 4. And we're asked to find the first, second, third, and fourth derivative. When I take the first derivative, I'm going to be looking at the function. So this 5 will come down in front, and I get 15x to the fourth. Then the 4 comes down in front, and I get minus 8x to the third. Then the 2 comes down in front, and I'm left with 2x. When I take the derivative of the 10x, I'm left with the minus 10. And then this 4 disappears because we're taking the derivative of a constant. So here's our first derivative right here. Now, if we need to find the second derivative, we're going to take the derivative of the first derivative. I would bring the 4 down in front and just repeat the process. When I bring the 4 down in front, that's going to give me 60x to the third. When I bring the 3 down in front with the 8, that's going to give me minus 24x squared. When I take the derivative of 2x, that's going to give me 2. And then when I take the derivative of this minus 10 here, it's going to disappear because we're taking the derivative of a constant. Now, if we take the third derivative, I'm going to take the 3 down in front. That gives me 180x squared. The derivative of this term would be minus 48x, and then this 2 would disappear. The fourth derivative, I take the 2 down in front, so I get the 360x, and then when I take the derivative of the minus 48x, I get minus 48. So when you talk about higher order derivatives, that means you're just taking derivatives of derivatives. Let's look at this next example. The question is giving us the function f of x is 1/2 x to the fourth minus 4x squared. We need to find the value of the function at 2. We need to take the first derivative and evaluate it at 2. Then we need to find the second derivative and evaluate it at 2. Here's our function. And when I take the first derivative, I'm going to bring the 4 down in front, which is going to give me 4 times 1/2, which is 2. And I bump my exponent down to 3. The derivative of 4x squared is going to give me 8x. And of course, I carry down that minus. So now here is our first derivative. Now to find the second derivative, I have to take the derivative of the derivative. So the 3 comes down in front, that's a 6, and then x to the third becomes x squared. When I take the derivative of 8x, that becomes 8, and of course bring down the minus. So now I have my first derivative and my second derivative. Now if we evaluate all 3 of these at 2, here's what we'll have. So when I want to find f of 2, that means I'm going to take 2 and plug it into the function everywhere I see x. So I'll have 1/2 times 2 to the 4th minus 4 times 2 squared. And when I clean that up and use my order of operations to find that value, I'm going to get a -8. When I evaluate the first derivative at x equals 2, that means in the first derivative, everywhere I see x, I'm going to replace it with 2. So that's going to give me 2 times 2 to the third minus 8 times 2. And when we clean that up, we're going to get 0. Lastly, when we evaluate the second derivative at 2, that means in the second derivative, everywhere I see x, I'm going to plug in 2. So that gives me 6 times 2 squared minus 8. And when we evaluate that, we get 16. For example 3, we're given that g of t is equal to t to the third minus 9t. We want to find the values of t so that g of t is equal to 0, g prime is equal to 0, which means the first derivative, and g double prime, which is the second derivative of t, is equal to 0. In example 3, we're given a function g that's defined as t to the third minus 9t, and we're asked to find the value of t when the function is equal to 0. We're asked to find the value of t when the derivative or the first derivative specifically is equal to 0. And then for part C, we're asked to find the value of t when the second derivative is equal to 0. So first we need to find the first and second derivatives. Here's our function. So when I take the derivative of my function g using the power rule, I'm going to get 3t squared minus 9. When I take the second derivative, which is the derivative of the derivative, I'm going to get 6t. So now for all 3 of these, for part A, B, and C, we need to set all 3 of these equal to 0 and solve for t. So when I set the function g equal to 0 and I solve, I can set it up by factoring. I want to set it up first where I set it equal to 0, where I have t to the third minus 9t is equal to 0. Then I can factor out a t from both terms. What's left inside after I factor out the t is the difference of squares. I have t squared minus 9. So then I can factor that a second time and write that as t plus 3 times t minus 3. So what this tells me is that my function g is going to be 0, meaning it's going to cross the x-axis at t is equal to 0, t is equal to -3, and t is equal to 3. Now, when I set the first derivative equal to 0, I'm going to have 3t squared minus 9, and I'm going to set that equal to 0. And then when I solve for t, because this is a quadratic and because of the way this is formatted, I can just isolate the t squared and find the square root of both sides. So I'm going to add 9 to both sides, divide by 3, and then take the square root of both sides. So I'm going to get plus or minus the square root of 3. So the first derivative is equal to 0 when t is equal to plus or minus the square root of 3. For the second derivative, I'm going to set that equal to 0. So I'm going to get 6t is equal to 0. So t has to be 0 when the second derivative is equal to 0. Now we're going to look at what the second derivative means in terms of a graph. and then I'm going to extend that idea, and I'm going to explain to you what it means in the context of a problem so that you can make sense of this. So when we look at this graph, it's broken up into 4 intervals. When I look at this first interval here, I'm going to start tracing it left to right. As I'm coming left to right, I'm going down. So on this interval, the function is decreasing. And remember, the derivative is the rate in which the function changes. So if I'm decreasing on this interval, that means my first derivative is going to be negative. Now, this is our cutoff point, and then when I go from here to here, I'm increasing. So that means on this interval, the second interval from here to here, I'm increasing, which means the first derivative is going to be positive. That's this here. Now let's look at this next interval. As I continue to go left to right, I'm increasing. So on this third interval from here to here, the first derivative should be positive because we're increasing. And then when I look at that last interval, as I trace it left to right, I'm going down. So the first derivative should be negative, indicating that that's an interval of decrease. So that we're familiar with, so that should be a review. Now let's look at what the second derivative means. The second derivative tells us the rate in which the first derivative is changing. And when we look at that graphically, that's indicating the way that the graph is shaped in terms of concavity. So if the second derivative is positive, that indicates that you're on an interval that is concave up. And if your second derivative is negative, that indicates that you're on an interval that's concave down. So if I go back to the beginning again and I trace this left to right, if I start here and I'm going left to right, from here to here, this is concave up, this whole interval. Then at this point here, it switches from concave up to concave down. This is called your inflection point. This is where it switches to concave down. So on this interval, since it's concave up, my second derivative is going to be positive. So both of these are going to be positive. Then on this interval right here, since it's concave down, the second derivative is going to be negative on these two intervals because they're both on that interval that is concave down. Now let's look at the breaking points of these intervals. This point right here that splits the first and the second interval, this is at a local min. As I come across here to here, my first derivative is negative because I'm decreasing. On this interval here, the function is increasing, which means my first derivative is positive. At this point right here, the function is neither increasing nor decreasing. So at this point here, the derivative, the first derivative, is going to be equal to 0. Remember what this means in terms of tangent lines. The derivative is the slope of the tangent line at that given point. And if I look at the tangent line right here, that slope of a horizontal line is 0. So that's why my derivative here is 0. So that point is where it cuts it off from decreasing and then switches to increasing. Same thing works for local maxes. This local max here indicates where it's going from increasing to decreasing. So from here to here, it's increasing, and then here to here, it's decreasing. This is the cutoff point in which it switches. So this point right here, the first derivative is going to be 0 because at this point, it's neither increasing nor decreasing. Looking at the second derivative, our cutoff point for where it's going to be positive, negative, is going to be the inflection point. On this interval from here to here, it's positive because it's concave up. And then on this interval from here to here, it's concave down, so the second derivative is going to be negative. Now that we've gone through an example of each case where we're looking at the signs of the first and second derivative, let's look at this in terms of speed and acceleration because that's what we're familiar with. And so we can think about it intuitively. So our function is going to be the distance function. So when we take the derivative, it's the rate in which the distance changes, which is our velocity. When we take the second derivative, that's the derivative of the derivative, which means we're looking at how the velocity changes. So if we look at this graph A, as I trace this left to right, you can see that the graph is increasing. The way that this graph is increasing, as it goes left to right, it's increasing faster over here. So the rate in which the velocity changes is increasing. That's our acceleration. So that means our acceleration is increasing, which means it's positive, and it should be on an interval that's concave up. When we're looking at example B here, or graph B, as we go left to right, the graph is still increasing, which means we're speeding up. However, as we go left to right, it starts to flatten out. So it's not increasing as fast as we go left to right. This tells me that the first derivative is positive, but the second derivative is negative. Also, you can tell by looking at the fact that this is on an interval that's concave down, verifies that we're looking at the second derivative as being negative. Looking at example C, or graph C, as I go left to right, the graph is decreasing. So that means the first derivative, which is the velocity, is going to be negative and it's slowing down. Because this is on an interval that's concave down, I know that my second derivative is also negative. So the velocity is going to decrease, but it's going to decrease faster and faster and faster as we go left to right. In example D, we're going to go left to right. This is still decreasing. So the velocity is going to be negative. But if we look at the second derivative, this is on an interval that's concave up. And as we go left to right, it starts off as slowing down faster, but as we come down, it's leveling out. So the rate in which the velocity is changing is slowing down. Let's look at example 5. It says, suppose the function c of t represents the amount of money in thousands of dollars that a county spends on the local drug war T months from January 1st, 2000. So this is saying that t is equal to 0 is our starting point, which represents January. Interpret this information provided using the fact that we know that the first derivative of the cost function evaluated at 15 is 1.6. And then the second derivative evaluated at 15 is negative. So that means here's a picture of the graph, what that looks like. Remember, t, the time in months, is going to come across the horizontal axis, and the cost is the vertical. So as I come across here, this clearly shows that from month 15 to 16, there's an increase in the cost. But if you notice, as we go left to right, it's increasing more slowly. That's where the second derivative comes in. Because the second derivative is negative, we know that graphically it's on an interval that's concave down, which if you extend the graph and kind of picture this, it looks like it's on an interval that's a bowl shape upside down. And then, but another way to look at it too is because the second derivative is negative, the rate in which the derivative is increasing is slowing down. So that's why this is slowing down and starting to flatten out up here. It's not increasing as fast. So the official interpretation is that 15 months from January 1st, 2000, the cost of fighting the drug war is increasing. However, it's increasing at a decreasing rate. This means that the citizens of this county can expect that the cost of fighting the drug war will still increase each month, but they can expect that each monthly increase is going to be less than the previous increase. Let's look at example 6. It says, suppose the function w of x represents the amount of money in thousands of dollars a county spends on welfare each month, where x is the number of people in thousands applying for and receiving welfare. Interpret the information provided by, this is saying that the first derivative is negative and the second derivative is negative. So this means that when the number of people that are applying and receiving welfare is 16,000, because it says it's in thousands, the change is going to be -8, and the second derivative is the change of the change. That's negative. So the way that we would interpret this is that at the time when 16,000 people are applying and receiving welfare, the citizens of this county cannot only expect the amount of money each month on welfare to decrease, but each month the decrease will be greater than the previous one. It's decreasing at a faster rate. So if you look at the graph, going from left to right, this is on an interval that's concave down. So the second derivative should be negative. And then also when we go left to right, it starts off slower and the decrease is getting more and more steep. So the amount of decrease is increasing. In the last example, example 7, it says, suppose the function a of t represents the amount in square meters of water hyacinth growing wild in a lake t months from the beginning of a university research project at the lake. Interpret the information provided by the first and second derivative. So the first derivative is negative, meaning there's a decrease of water hyacinth growing in the lake. The second derivative is positive, meaning that this is going to lie on an interval that's concave up. If we look at the graph and we trace it left to right, if we go from 25 to 26, it's decreasing in the number of these plants that are growing wild, but it's leveling out as we go left to right. So the rate of the decrease is getting slower and slower. So the official definition is that 25 months after the beginning of the research project, the amount of the water hyacinth in the lake is decreasing, but at a decreasing rate. This means that although the amount of the water hyacinth in the lake is decreasing each month, each decrease will be less than the previous decrease. All right, last slide. I wanted to show you the command for checking derivatives that are of higher order. So here's an example of what that's going to look like. If you put in GeoGebra your original function and you use the command that says derivative, there's going to be two options. One option will come in where you can put in the function. Another function will come up where it says you can put in the order. When you put in the order, that just tells you what order derivative. So if I put in derivative of f, comma 1, that's going to tell GeoGebra to take the first derivative of f, which is x to the 5th. And there it is right there. We bring the 5 down in front and we raise it to the 4th power. If I wanted to take the second derivative, then I would have to use the derivative command and then choose the f function and then put in comma 2 because I want the second derivative. That means I'm taking the derivative of the derivative. So if I look at this, I take 5 times 4, that's 20, and then I decrease the exponent by 1. So this is my second derivative here. So this is a nice way when you're doing second derivatives or even higher derivatives, you'll be able to check your answers.